Okay, so thank you very much for your invitation. So this talk is about pure untyped lambda calculus and church numerals. So I'm sure everyone is been teaching or has been teaching this subject and can, for example, tell offhand the expression for successor in church numerals. Maybe some can even tell the two expressions for the successor of church numerals. But what about three expressions? Incidentally, can somebody tell three different expressions for successor? But the point is about the predecessor. So they probably it would be difficult to tell offhand the expression for the predecessor lambda numerals, or church numerals. But what about two different predecessor expressions, so three different predecessor expressions? That may be a little bit difficult for many people, I think. And hence, this is the talk. So, as I said, that we are talking about pure untyped lambda calculus. There are no constants, there are no types. So I would use the notation C, C0, etc. For church numerals. So in general, that nth church numeral is represented, or nth numeral is represented as nth repeated application of f, some function f to x. So the successor is a term that, given a church numeral, returns the next numeral. And so here the one of the expressions for the successors. And so the predecessor is the, well, does the reverse. So given a numeral for n, for 1 or etc., to return the previous numeral. So it's an open question what to do when predecessor is applied to 0 when there is no previous numeral. So, well, I mean, there is no agreement what to return, so whichever works, I mean, open choice. So this is the question, is to find the expression for predecessor. I mean, hopefully not 1, but 2, 3, or more expressions for the predecessor. So, I mean, the main question is, why would anyone care about it? So, well, first of all, it's a very good puzzle. So even Church was stumped for a while. Well, actually, he was stumped, and it only Kleene unstumped him. So the second is a very colorful story. So you heard this, I mean, written in many textbooks about, well, Kleene getting his tooth extracted, and when he, I mean, discovered this predecessor, I mean, got the idea for predecessor while under influence of nitrous oxide. So it's also kind of adds to the challenge is that the commonly, like for example, in types and programming languages, tuple, that they explain Kleene, when they explain the Kleene predecessor, Kleene story, it's called very tricky. And so it's invariably called on many websites, the predecessor is called very tricky. And it takes a while to explain. And actually in tuple, it takes half a page to explain. And tuple is a very, I mean, large format book. What's more interesting is that the Kleene predecessor is actually one of the worst predecessors in every metric. It's hard to explain, it's hard to fit on one line, it's not very efficient. I mean, whichever metric you choose is one of the worst. And mainly that searching for the predecessors turns out very insightful. And hopefully I hope to demonstrate in this talk. Well, perhaps it's worth answering another question of why did I care about the predecessor? So back in the last century, when I first learned lambda calculus, I was fascinated and puzzled. Well, the natural number is represented as a repeated application of some function. So its successor has to add the application, so which is very easy to do. But then it follows the predecessor have to remove the application. And that didn't seem at all easy to do because, well, there is no application operation for unapply in lambda calculus, and there is no operation to deconstruct the terms. So I was puzzled, and I was thinking for 2 days, and eventually I discovered the predecessor. And here is that, the expression that I discovered. Incidentally, I don't think that you've seen it before. I don't think anyone has seen it before. So it's, it's a different from, others that I know. Incidentally, I should mention that it was in 1992, and that year I also got a tooth extracted. So it seems to be there was some kind of curse associated with predecessors. So you need to, sacrifice a tooth to learn the truth about them. So 25, about quarter century afterwards, after this incident, I was, I have become an associate professor of Tohoku University. Assistant professor at Tohoku University. Assistant professor in our university is a very nice sounding title for postdoc teaching assistant, so which is what I am. So my duty is to assist high-ranking professor, associates and professors. So one of the duties is we have study seminars in our lab, and which is conducted by associate professor, and I have to attend the seminar and assist. So, well, I have to attend, but nobody asked me what to do, how to assist. So I just have to sit them and do nothing, which is very boring. So one day I was, attending the seminar, listened to students explaining Kleene predecessor because, well, it was a seminar studying types and programming languages, tuple. And I remember thinking that, well, it's so complicated, and could I possibly do better than that? Well, and I remember that I was bored. I had nothing else to do. So, I tried to do better. I was quite surprised that I quickly, found 2 other predecessors and even wrote them on the margin of tuple. By the way, tuple has very wide margins. So that's how this, paper, one thing led to another. There are more predecessors came up, and that's how the paper, ended up with this paper, ended up with this talk. So that's the story.
Can I ask a question?
Yes.
The church encoding is typable in simply typed lambda calculus for church numerals. Are all of your predecessors typable too, or are some of them not typable?
No, it's actually proven that predecessors are not typable in simply typed lambda calculus. Right,
you have to add, but you can add other things to your type system that will allow them to be typed then.
Yes, but it's, well, if we call simply typed lambda calculus as just, by classical definition, simply typed lambda calculus. Yes, you can add more. For example, you can add polymorphic types, and that would also help, right? So.
Right. Okay, thanks.
Okay. Yeah, but in case Ohad didn't say that, please, if there is a question, please tell me. But please say it, because on one screen I don't see anyone, or I don't only see my slides, so I'm kind of doing it a little bit blind, so I can't see anybody raising hands and so forth. So please say if you're asking questions. Okay. So here's the summary of the paper, and the talk. So this predecessor is a representation change problem. And the main result is that not 2, not 3, but actually 6 predecessors in plain sight. All except 2 are new. So, well, one of them is the Kleene predecessor, and the other one, which is also known, I'll mention it later on. All of them have normal forms, and of course distinct normal forms, because they're all different. And there are, more interesting, the methods. So there's 2 general methods which extend beyond numbers. So using this method, you can find predecessor not only on any algebraic data type. For example, for trees, where the predecessor is getting the left branch or the right branch or something like that. And there are several specific methods. So they don't generalize too well, but on the other hand, they are more elegant, and one of them is particularly elegant, and I think this is kind of nice contribution of it. Okay, so main idea of the approach. So the fundamental tautology of church numerals is very easy to overlook. Well, hopefully it's obvious, right? So if we have a church numeral and we, so number n is n times successor away from 0. So if we move away from 0 n times, then we arrive at this number. So it seems to be obvious, right? So hopefully, it's controversial. And we will see this expression over and over again through the talk. And so it kind of, we'll see that it's much deeper than it appears. And hopefully we will see that eventually that expression deserves the full slide dedicated to it. Okay, here is the first appearance of this new appearance of this expression. So that's previous expression is the equality. So the left-hand side and right-hand side are equal, and this symbol which I use dot equal, it's the beta congruence. I don't use 8 equality, it's only beta. So beta congruence. So if we introduce, make slight modifications. So we replace suc and C0 with some new terms, sup and P0, which are just 3 parameters. So this, can be considered to be as a definition. So it defines some, terms Pn, and depending on n, so we define a family of terms, a sequence of terms. So we can, so we have the sequence P0, P1, P2, etc., a sequence of terms of P numerals, I sometimes would call it. Well, obviously P0 is the initial element, right? And so this is the meaning of the parameter P0. So this sup is the step function. So it's easy to see that sup applied to Pn gives the next Pn.
Oleg, I have a question.
Right?
Okay. So you're fixing some collection of church numerals, or are these the church numerals? What is this?
No, Cn is the church numeral.
Okay, the usual ones.
And P0 is just arbitrarily parameter free, so far unspecified. So therefore I get a new sequence P0, P1, P2, Pn, etc., right? Each corresponding to one church numeral. Then P0
but only P0 is the parameter, right? Pn is you just defined it now, right? So the only parameter is P0.
Yeah. Yes. So okay, P0 is the is the initial element, right? Of course, it's consistent, right? So if I plug 0, then sup is the step function.
Oh,
so
step.
Okay. To see that apply sup to Pn, it would be Pn plus 1, right?
Yep. Thanks.
Okay. I can read it conversely. So if I just have P0 and sup as a parameters, that this expression 2 stars gives the closed form for the nth element of the sequence, right? Okay. So here is the general recipe. So it's a representation change. So the idea is that finding predecessor in church numerals is difficult. So let's move to a different representation where it's easy. So remember that sup and P0 are 3 parameters, so we can choose, we can, as we wish, and so we can get, the desired Pn. So if those Pn happen to be such that the predecessor, this that maps Pn plus 1 to the previous function, and the projection that kind of projects Pn to the corresponding Cn are easy to define, or on the other hand, if they're just their composition that maps n plus 1 P number to nth church numeral is easy to define. Then the predecessor is this expression which is written on the slide. Right, so we, convert n church numeral to P number, and then from that number we project previous Cn. So now the task is to find this, suitable sub and P0. And here is the first application, is the church Kleene predecessor. So let's take Pn as a point between two consecutive numbers, Cn and Cn minus 1, and represent it as a pair. So in here, P0, when I write C minus 1 is the term that you choose to be a, predecessor of 0, so arbitrarily term. So you can choose C0 or any other term you wish. So here we got P0, P1, P2 is that number between 1 and 2. It means pair of C1 and C2. Then the P0, so we have two parameters. Well, P0 is, obviously it's on the slide. And the sub projection is, if we move from P1 to P2, then it's obvious that the second component of P1 becomes the first component of P2, and the second component of P2 is one greater. So this is a sub. And projection is, it's the first. So where second, first, and pairs is the, standard. We just use standard encoding in lambda calculus. So if you plug it into...
Can I ask a question?
Yes.
What is C minus 1?
Arbitrarily term.
It can be anything at all, I see.
Choose whichever. Here on the slide, choose whichever you want.
Right. Thanks.
Okay. So if we plug everything and expand all the abbreviations, then we get the expression at the bottom of the slide. So it's obvious that the drawback of the Kleene predecessor is obvious to see, right? It doesn't fit on the slide. So that is one of the biggest drawbacks. There is another slight uneasiness. So if we look at the sub expression, we see that it uses second components of the pair, but it doesn't actually use the first component of the pair. So it kind of crosses the mind. Maybe it's slightly over-engineered. Okay, here is even better general recipe. So I said before that the general recipe for the predecessor is this expression on the, on the top of the slide. So where proch pred should be this mapping, which should be easy to define. And the simplest, easy to define proch pred is to be an identity or the sort of an identity. So let's this numbers P be such that Pn plus 1 is isomorphic to Cn. So the numbers P and church numerals are isomorphic with a shift by 1. So now the task is to find P0 in sub that, go with it. And so the plan for the next, what is this expression which I called by tilde? So in general methods which I explain, tilde is a bijection. And in some specific method which I explained, tilde is the identity. So this Pn plus 1 is actually the church numeral themselves. Okay. So now we're general methods. So as I said, the idea is to find, so that P numerals are isomorphic to church numerals. So it's a sequence, each is isomorphic to church numerals, but with a shift. So that Pn is, corresponds to C0, P2 corresponds to C1, etc., etc. So it means that we have the same sequence, but plus we have one extra element P0, which doesn't correspond to any church numeral. Well, so there is one general method of how to add extra element to the set, right? It's an X option method. So, previous elements map into sums, like C0 maps to some C0, C1 some C1, etc. And none is this extra element. Right? It's obvious that P1, Pn plus 1 is isomorphic to Cn, or there's a bijection to Cn, right? It's just add or take sum. And P0 is just, that's one thing extra. So just looking at the sequence, that the step function is, well, easy to see. I mean, like on the slide. So if P happens to be none, then the next should be sum C0. And if P is sum C, then the next would be sum successor C. And so the predecessor is, I mean, I know, extracting from sum, just removing sum, and a little bit sloppy notation from sum. If actually the argument isn't sum, then it would choose arbitrarily term to return. Like it's from sum with default. Well, that's the recipe. And now if we use standard encoding of option in lambda calculus, like none is, well, this term, sum is this term, then this encoding lets us deconstruct to analyze the term, which is sum or none. So therefore, I mean, we have this expression for sup, and the predecessor becomes this expression. And if we expand all the abbreviation and normalize that, we get what's written at the bottom of the slide. As you can see, there is a progress. It actually fits on the slide, unlike Kleene predecessor. So far, no questions so far? Okay. There is slight optimizations we can do. So here again, our Quan. Well, the right-hand side or left-hand side is a church numeral, and so right-hand side is also church numeral. And we know all church numerals start with lambda f, lambda z, right? So we can write this expression in this form. So where instead of successor and C0, we use kind of different expressions, I subscript FZ, which use F and Z as parameters, as free variables. And it's easy to see which of those successor and Z should be. Well, successor is just F, and well, C0 is Z. Again, there should be no doubt about the truth of this expression, right? So now we can kind of redo what we have done, but using this subscripted F and Z. So this is the previous slide we had before, unsubscripted. So this is a derivation. And now we do subscripted. So the predecessor, as you can see, now become lambda FZ. And now everything has from, sum of Z, sup of Z, none of Z. So none of Z is, well, because Z is already available, then it's kind of easy. Then it's, I mean, lambda K returns Z. There is no need to find it, take it as an argument. It's already available. Well, sum of Z doesn't happen to use neither F nor Z. And sup of Z, I mean, I know this expression. And so the predecessor works out to be, I mean, well, like before. And if we desugar, we get this very short expression. So this expression is, it's actually the shortest predecessor ever known, well, so far. I haven't seen anything shorter. And actually turns out to be the fastest as well. It appears, so this is the second one, which is, I mean, unknown. It appears in Barndrecht book and in Barndrecht tutorial. And it's given, the credit is given to Veldman, but there is no, neither in the book nor in tutorial, there is no derivation, no proof of what, I mean, no, whether, I mean, how to get it and whether it's correct or not. It simply, Barndrecht simply says, well, this is the, I mean, the Veltman derived another expression. It doesn't actually give citation either. So now we see how this expression is derived. And actually it's, I mean, I know probably we won't have time for that today, but in the paper, I show that this approach generalizes and beyond church numerals. So it generalizes to tree and to other algebraic data types. So this is derivation. So this is not only derivations for church numerals, this is derivations for arbitrary data types. Any questions so far?
Yeah, question. When you say fastest, is this a matter of complexity or what?
Yes, I mean, no. I don't know. I mean, no. I thought I will have not time for that. So, although it's not, I mean, no, hardly anybody cares about the speed of predecessor, but I timed it. So, I checked how much. Well, it takes linear. I mean, no, predecessor takes linear time, of course. So that's another thing that's known, right? So there is no constant time predecessor. It also, I mean, it either linear time or, I mean, worse. So the worse it's getting linear. So I checked time it takes to normalize using normal order reduction and just counting number of reductions.
Okay, yeah.
And I also checked, so if we embed it in share scheme, which is the fastest scheme system, now it's called by value, and how long does it take to derive predecessor of like 100? So I tried called by name and normal order and call by value strategy. And either of this, in all of the tests, it's the fastest and takes the least memory.
Okay, thanks.
I have a question, if I may.
So,
sorry?
oh, okay. So I heard that there was a question.
Yeah. So you arrived at this optimized form by doing the subscripting trick.
Yes.
With FNZ. Is this some kind of memoization on the applications that will certainly happen, and you kind of remove them? What's the intuition behind it?
Okay, I mean, here's one intuition. I mean, although probably not the one that but maybe some people like it. So this there, I mean, a previous slide, right? So here we have, I mean, some and none. You can see it looks like a continuation passing style, right? To some people. Like K, and that's why I actually use the number, K as a continuation.
Right.
So none is, so in a sense, what we do, I mean, you can think, how do you find continuation? Then 0 corresponds to sort of to exception, right? So we throw the exception, and everything else is just, I mean, so each number, so you can kind of think about the construction that each number maps to itself, and the -1 is the exception. And so when we going to increment the exception, then we throw exception, then we need to handle it somehow. And when we increment the number, then we increment the number as it is. So when the none is in this unoptimized, it takes continuation and takes this y, which is that, that's the exception, so to speak, to race. And here none of z. This is the more optimized encoding of the exceptions, right? So it takes the continuation and it doesn't invoke the continuation, right? So it just returns z immediately. So in a sense, you can, I mean, imagine writing this predecessor in calculus with exception and just mapping -1 into raising the exception. And the sub includes the catching of exceptions.
Okay, thanks.
So, I mean, sum is, you can, I mean, very easy to see. It takes the continuation and takes, and immediately apply, I mean, continuation to its argument, right? So, I mean, it's obviously what it, and none is the, I mean, is the exception. So in this encoding, especially kind of the exceptional nature of -1 shows very clearly. Actually, even wanted once actually to write this using raise and and return. Yeah, so sum is just return and none is the raise. Okay. So now we are going to, talk about specific methods. So this was, general methods, one general method, and it's, an optimization would be another general methods come up, but in the middle we look for specific methods that work for church numerals but don't easily generalize. So in this method, as I said, that Pn plus 1 is church numeral than Cn itself. It's not just isomorphic, it's just itself. So P0 is, well, it's something else. It means, well, I would write C minus 1. So because this projection function is the identity, well, then the predecessor has this particular form, right? So it, iterate successor plus. Where successor plus is the function which is successor on church numeral. So if the argument is the church numeral, it should, it should be just a successor. And the exception is if the argument is minus 1, then it should return C0. So now the task is to find C minus 1 that can be distinguished from any other church numerals. Well, and how do we usually go about solving this task is to exploit some invariant of church numerals, right? That holds for all church numerals. And here is one invariant of church numerals. If you apply church identity function is the fixed point of church numerals, right? So if you apply church numeral to the identity, you get the identity. Then, how do we get C minus 1? It should be a term which applied to identity returns something other than identity. And well, here it's a good choice shown on the slide is this function. Then successor prime takes this expression and the whole predecessor is, well, shown at the bottom of the slide. So this is the predecessor that I found 30 years ago. Okay. There are, many ways to, play around and optimize. And in the paper, I mentioned a couple of ways, and the accompanying code has more, playing around this way. So actually, the number of new predecessors is not just, well, 6 minus 2, 4, but actually, I have many, many more predecessors. So you can play around and find whichever works, whichever shorter, whichever faster. Okay, and here's my favorite predecessor. It also goes along this line, but my favorite because it's very easy to explain, very easy to define. So here again, our koan. It's obvious, right? So hopefully this expression is also obvious. So if we start, moving away from 0 and times, then we arrive at this number. And if we start from 1, then we add up one further number, right? So therefore, this term which I write, successor with a circle, is the successor, right? Because so it takes n and applies successor C1, then we get the next number. So it is a successor of church numerals. So this is the third, I said that, ask at the beginning, could anyone name third expression for successor? So this is the third expression of successor in church numerals. But of course, we can apply it to things other than church numerals, right? So for example, if we apply it to this particular term, so that takes two arguments, ignores them, and returns C0, then it's obviously the argument, the result would be C0, right? I think it's obvious, right? So, well, if the result of the successor is C0, then it stands to reason that the argument of the successor is the -1, right? So that this term lambda fx C0 is, I mean, it can be thought about is of -1, and the acts as -1 in this context. And so here is the predecessor. So I mean, how do we get predecessor? Then, I mean, and it follows this, I mean, previous pattern. So if we start counting from -1, so I mean, it's the second expression. If we start counting from 1, we arrive at the next number. But if we start counting from -1, then we arrive at the previous number. So here is this expression. So I like it because, well, in types and programming language, the tuple, it takes half a page to explain Kleene predecessor. And it's still, I mean, there isn't any, well, it kind of explains how it works, but doesn't even, well, one might still have kind of doubts whether it's correct or not, or there is something missing. So it's not obviously, I mean, clear how it works. But here it takes only 4 lines to derive the predecessor. So here's the whole derivation. And hopefully each of those lines up, I mean, patently obvious. So there is nothing to prove. So here's the most easy to explain derivation of the predecessor. Any questions so far? Incidentally, the notation is chosen deliberately, that circle. So that successor circle is the meta-circular successor, right? It uses the underlying successor of the object language, so to speak. So that the trick in the meta-circular successor, so we raise the level to the meta-programming, and in a sense extend the domain of the successor. So now the successor accepts what can be applied usefully to other terms, and these other terms, it turns out, -1. So the original successor is, I mean, I know if you play around, it doesn't seem to be possible to apply it to something, then it gets C0. But with this meta-circular successor, it's just obvious what should be the term to get C0, how to get the result C0. That's one of the lessons, just raising the level. Okay, so as I said before, that I was puzzled by an application. So how do we get, so the predecessor has to unapply a function, and how do we unapply a function if lambda calculus does not support this operation? Well, the trick is, again, change the representation. So instead of fn of z, which is an n times repeated application of f to z, we use a different representation. I will use p n z. It's n times iterated sum applied to none, and all indexed by the z. Where none is, well, actually, I mean, these are the same expression we saw before in the optimized version. So the non-z is kind of the exception strong z, and some z is this one. Why they're useful? Well, I mean, it's obviously we can p and z and cn are, well, at least fn of z, they're isomorphic, right? We just, I mean, can replace, well, actually, I'll talk about it slightly later. So now we can do pattern matching on this. I mean, if we, for example, if we apply to p and z identity, we get the previous number if n was positive, or we get z otherwise. That's quite clear, right? So it's possible. Yes. There's a question.
I think there isn't a question.
Okay. So if I so these P and Z and Cn, they're kind of isomorphic to church numerals. So if we have a church numeral that we can convert to P and Z, and this can be called reification, and here is the term which you're doing this. And it's also clear that from P and Z we can do this, get repeated applications of some function f to z. And this is done with the term reflection, which reflection is the interpreter which interpret this repeated application of sums and replace each sum with f. Here that fix appears in red, right? So this is kind of red flag because, well, it seems to be not a, the term isn't going to have a normal form. But here's the trick, I mean, So if we have P and Z and we want to replace all sums with M, so we need to perform iterations, but we need to perform iterations only n times, right? Because there is n or n sums here, so we need to iterate n times. And then the observation is that church numeral itself is a finite approximation to the fixed point, which iterates, well, n times and then the stops. So if instead fix we use the church numeral itself, Cn, then it would do just right amount of iteration. So I would show the result here on the slide, but so the predecessor would, would be a composition of the reification, reflection, and this application of the identity that gives the predecessor. So that would be the result. And in the reflection, instead of fix, I would just use the number n itself. So it's one might think that this is a kind of piling up reification upon the reflection upon predecessors would be very slow, but in fact it's actually one of the fastest predecessors. So it actually works quite well. Okay, so coming to the conclusions. So let's look back and see what what things we have seen over and over again. So of course we have seen algebras, right? So with operations variously called C0, P0, C1+1, C-1 with arity 0, or successor or support with arity 1. So, or you can write in functor form this algebra fx 1 plus x. And well, church numerals are the initial algebra of this signature. So then we saw that x option or sum and none appear all the time. And of course, now it's clear why any appear all the time, because x option is just this functor f. As I said, well, church numerals, they're initial f algebra of this functor. So, well, for initial L algebra, for each initial algebra can be mapped uniquely to any other algebra of the signature, to any other algebra with with operation sub and p0. And so our operations plus star star was that unique homomorphism. Well, initial algebra can be also, mapped. There is homomorphism of initial algebra to itself. And because it's a unique homomorphism, that it must be identity homomorphism, so that the star, our Quan has been expression of that law. And these ideas generalize and to arbitrary data type, not necessarily 1 plus x. So if you want to find a predecessor or something like a responsive deconstructor on church encoding of other data types, so what one needs to do is to first write this f functor, then apply the Bernoulli-Scott-Morgensen encoding Actually, first, when the first general method I explained, it was essentially Bernoulli encoding. And this unapplication reflection verification trick was actually Scott Mogensen encoding. And that's it. And so we automatically mechanically obtain efficient predecessor extractor for this data type. And in the paper, I do this for trees with some values in the leaves. And well, you can do it for any data types you want. Well, specific approaches which specific to church numerals, they don't generalize that well, but on the other hand, they are, well, they're nice. So in the paper, there is also, as I said, there is a generalization and illustration how it works for trees, not only for church numerals, and there are also outlines of their correctness proofs. So the proofs, of course, you can prove it by induction, but that isn't that nice. So the proofs that I outlined are all algebraic equation proofs. There are some lemmas which need to be proven either by induction or maybe categorically, but the rest of the proofs are purely algebraic. And well, in the conclusion is probably nice. It's good to quote Jean-Luc Picard that there must be, all this might be an elaborate simulation running inside a little device sitting on someone's table. And this metacircular successor is, I think, particularly apt to this quote. So, well, that's the conclusion is that it's, I mean, I don't know, if you think as what Captain Picard was thinking, then maybe that the difficult problem of finding predecessor, which required previously 2 sacrifices and using some substances, turns out to be very easy. Well, thank you very much.
Thanks. Do we have questions?
Yes, I have a question, or maybe it's just, I will just ask for a confirmation at this point. So during your talk, there were a couple places in which I realized that a specific thing was happening. In the first instance, you mentioned that you needed to unapply a function in a certain sense, and in another place you mentioned that you needed to find some C-1 such that you could distinguish it from all the other Cn. And,
yes.
When you said this, the first thing that I thought was BEM trees, right? And I was wondering whether when at the end you mentioned a Bernoulli technique that I'm not familiar with, that is related to that.
Oh, I got but to what? Could you repeat it again?
Yes. So the fact is that in certain situations you need to understand whether 2 terms can be distinguished from one another by some sort of manipulation. So and this could be useful both for unapplying and for or for finding that C-1 that is clearly distinguished from all of the other Cn. And what I thought is that in that moment was that maybe there is some technique involving BEM trees that could allow you to do that.
Oh, yeah. Well, I mean, no, in the general approach, yes, it's. I mean, no, indeed, I mean, no. Well, actually, it's one of them related to the Bernoulli encoding, but distinguishing. Okay, so. yes, it's actually, I mean, I know, I see in a sense, yeah, I mean, I know, when I have C minus, well, in the general approach where I have an application and so forth, it's very general, simply use the representation where I can perform deconstruction. So, but this is a very strong requirement. So the weaker requirement, I don't actually need to deconstruct the terms. I just need to distinguish C minus 1 from any other church numerals. And this is indeed, I mean, the Berm tree would be very helpful. But of course, I mean, I know I need to, in Berm tree distinguishes 2 terms, and now I have to distinguish 1 term from a family of terms, right? So it's slightly different setting.
Right. Yeah, I was thinking that as well. Anyway, thank you very much. Very nice talk, and I think that a number of these techniques should really be taught to students when we introduce them to the lambda calculus. Thanks.
Okay, thank you.
So there's a question in the chat. We can see natural numbers as lists of units.
Yes.
So if you move from unit to A, right? So not all the way up to trees, but just from list unit to list A. What do predecessors correspond to?
Well, head and tail.
Okay, thanks. And there's another question by Sam now. Sam?
Again, Oleg. So I asked you earlier this question about typing.
Yes.
It seemed to me that more or less all that's going on here could be done in a system. You don't need like full polymorphism. You just need inductive types with folds. And
yeah, well,
but also following on from that, there's a whole load of work in that setting. I mean, again, connecting to the initial algebra stuff on more sophisticated kinds of folds, sort of histomorphisms in particular, so course of a value induction. And that fundamentally seems to be what we're trying to do here. The way in which you compute the predecessor is you remember all of the sort of numbers you've already seen, and then you can just refer back to the history and pick the last one you saw. So it seems to me there must be connections between the work that people have done in that area and what you're doing here. I mean, have you thought about that?
Some of them, only some of them. The other methods are not kind of related to the iterations, right? So it's I mean, many of them, as I said, that exceptions is one particular way it's thinking about. There is no history. You simply need to distinguish, take one term which is different from all church numerals.
Right,
then
but you're still, I mean, what the church numeral does is compute a fold. But the predecessor has to be, as you said, linear in the best case.
Yeah.
So it still has to go through everything. I realize, yeah, you don't necessarily remember all of the history, but you are having to somehow.
Well, but it's, I mean, I know that's true, but say, I mean, I know one of them, doesn't need to be any history. You just, I mean, I know, maintain that. So if you simply manage to distinguish that C minus 1, then you maintain the last element and increment it, right? So you do step by step. So it is a really fold. Like successor, metacircular successor, it is actually really fold. There's no history in that. It is fold.
Right. Okay. But sort of connecting to my initial part of the question.
Yeah.
Do you have any examples here where you are actually stepping out of something you could type with inductive types?
Well, I haven't actually thought about types as well at all.
Okay, it'd be interesting to sort of to see what types. I mean, you can just type in your examples to OCaml or something and see what types it infers enable.
Oh yeah, I mean that would be recursive types. Well, actually, one of them I use Scott Mogensen encoding, right?
So that might be more interesting. Yeah. Okay.
So it requires recursive types, right? So we know what it. I mean, I don't know.
Right. Yeah, and then as soon as you have full recursive types, that's just the same as being untyped, pretty much. You can type any untyped lambda calculus term that way. Okay, but maybe with the church encodings, you don't require full recursive types.
Yeah. Well, I mean, that's Gerard's PhD, right? So I mean, in a sense.
Indeed. Okay. Thanks.
Are there any more questions? So I have a quick one.
Yes.
Or maybe more of a comment. I'm not sure. So there's three different. When we talk about this being able to distinguish between terms, right? There's different levels, right? So one is we want to generate different normal forms, right? But then we also want to be able to, as part of the computation, as part of the program, tell one of the normal forms from another one, right? And if they're different, do something, right? Or tell one apart from a class of them, and in response do something, right? The last kind of distinguishability, right, is you want to be able to to tell which one it is and return the corresponding church numeral, right? And I think you're using them in slightly different, using slightly different notions of distinguishability in different parts of your talk, right? So
it's
kind of a good way to organize this, right? Because it seems to give you some hacking power, right?
Yeah, well, it is correct because it kind of different methods that they have different requirements, right? So one of them does require deep deconstruction, and another doesn't actually require deep deconstruction. And especially like Scott Moggensen and Church that Bomber-Duch's encoding. Bomber-Duch encoding is more limited because you don't actually get to see the previous kind of from when you remove the constructor, you just get to see the the result of its interpretation. So it's one particular maybe worth mentioning is that this method, I meant it in related work. Okay, where is it? Okay, so this slide is mostly related to the kind of approach illustrated in Barendrecht book. So where he introduces numeral systems which are related, which are isomorphic to church numerals. But there are two distinctions of what this slide from Barendrecht book, because he really meant reflection verification to be inverses and really meant isomorphism, and he also used real fix, so his predecessor didn't have a normal form. But here, as you can see, the reflection verification by looking at the types, there aren't actually inverses. Well, the types do not match. So I try to find the weakest thing that I can get away with.
Okay, thanks. If we don't have any more questions, I suggest I'll
one last question.
Oh yeah, go ahead.
Yes.
So in your looking back slide, where you talk about algebras and factors, you come up with a functor 1 plus x, which is maybe or option, but I don't understand how you arrive at it systematically. In your looking back, one of the last slides, yeah.
Yeah.
I cannot hear anything.
Okay. No, why is it? Okay, now it is. Okay, good. Well, you can encode the signature. So the signature has two operations, one with arity 1 and another with arity 0, right?
Right.
And this is the standard encoding of the signature in terms of a functor. So there's two operations. So several operations are added plus, and then arity 0 is going to be 1, arity 1 will be x, and arity 2 it will be x times x, etc.
Right. Yeah.
So if, for example, there is for 3, I think I have a plus, so I have values of type a in the leaf. So the function will be a plus x squared. So a, it means because there's a value in the leaf, and x squared because there's a two, well, branches on the node. So that corresponds to node.
Right. But here, yeah, it's the maybe that corresponds to this functor, or the option.
Yes. Well,
it's not the numerals that you started from.
No, well, the numerals are the fixed point of the least fixed point of the functor, right?
So I guess the point here, right, is that Church numeral represent natural numbers. Natural numbers are the least fixed point for this functor. And so if you want to write in general for data type that's given by a fixed point, you take the functor for that data type and you encode it using Scott Morrison or the other one.
Yeah.
Right. Okay, thanks.
Sure. Okay. So that's why, I mean, if you generalize instead of X option, there would be that data type that, I mean, I don't know, shows up.
Yeah, I guess what I was confused by is the Peano representation of numbers is the same as maybe X.
Well, it's a fixed point of it, right? So maybe X is non-recursive.
Ah, right. Yeah.
And number need to recur. So that's the kind of so the functor gives the kind of shape, the outer shape, and to get the numbers you just iterate it upon, right?
Right. Great, thank you.